What if I told you that your phone's blazing fast internet isn't just powered by 5G or fiber optic cables, but by a mistake during a rainy day experiment, a retired Indian Navy engineer, and a mathematical breakthrough that turned a communication flaw into a superpower? That idea is called MIMO, short for multiple input, multiple output. A technology so powerful, it transformed the very foundation of wireless communication, enabling us to stream Netflix, scroll Instagram, or have crystal clear Zoom calls, all without wires. But here's the crazy part. Most people have never heard of it. Today, we unravel how a single insight changed the world. The story of how MIMO, a wickedly clever trick, became the backbone of modern wireless networks. Let's rewind. In the early 2000s, before smartphones ruled our lives, mobile networks had it easy. They were designed to carry voice signals, not data. A measly 8 to 10 kilobits per second was enough for that. From 1G to 3G, the focus wasn't on speed. It was about efficiency. How many phone calls could a single radio tower handle using the same limited radio spectrum? But then came the smartphone revolution. And with it came demand, massive, insatiable demand for wireless data. Suddenly, people weren't just calling, they were browsing the web, watching videos, sending selfies, playing mobile games. Data usage exploded. This created a massive problem. How could mobile operators increase data transfer rates without buying more and more expensive bandwidth? Cranking up signal power, something phones can't handle because of battery limits and health regulations? The solution? A breakthrough so simple, yet so powerful, it would change everything. The industry turned to MIMO, a technology that took the messiness of radio signals and used it to our advantage. Let's start with a mental picture. Imagine we're in a large room. I shout, "Hello," to you from the other side. That sound doesn't just travel straight to you. It bounces off the floor, the ceiling, the walls. Some of it arrives instantly. Some takes longer. Some sounds are stronger, some weaker. This is called multipath propagation. You've experienced this with echoes. In the world of radio waves, it's no different. But here's the problem. When multiple versions of the same signal arrive at different times, they can interfere with each other. If the peaks and valleys of the waveforms don't line up, they can cancel each other out. That's called destructive interference. In the early days of analog TV, this caused something called ghosting, duplicate shadows of images caused by signals arriving via different paths. For decades, engineers tried to eliminate multipath. It was considered a flaw. But some began to wonder, what if we could use it instead? Let's rewind again, this time to 1901. Guglielmo Marconi, the father of long-distance wireless, was sending signals across the Atlantic. They were weak, almost unusable. But he discovered something. By adding a second antenna, he could pick up a stronger version of the signal, thanks to different reflection paths. This concept evolved into what we now call antenna diversity, using multiple antennas to catch multiple versions of the same signal, and then picking the best one, or even combining them. Fast forward to the 1990s. Engineers began using multiple antennas not just for receiving, but also for transmitting. But there was a big problem. How would the receiver know which of the transmit antennas was sending the cleanest signal? Enter Siavash Alamoudi. In 1998, he proposed a clever scheme now known as space-time block coding. Two antennas would transmit two versions of the same data. But instead of sending them identically, the second transmission would be tweaked and swapped. Using simple math, the receiver could reconstruct the original message, even if one signal was weaker or delayed. This was the first building block of MIMO as we know it. But the real light bulb moment came not from a telecom giant, but from a former Navy sonar engineer from India. His name? Dr. Arogyaswamy Palraj. In the early 90s, Palraj was at Stanford University, experimenting with ways to separate interfering signals from aircraft. One day, a sudden rainstorm forced him and his students to move their outdoor test indoors. A student carried two cordless phones into the building, both in the same hand. Yet, surprisingly, Palraj's system could still separate the signals. How? He quickly realized. The indoor environment caused reflections, multipath propagation. In that moment, Palraj saw what others didn't. Instead of a nuisance, multipath was an opportunity. By placing multiple antennas at the transmitter and receiver, each signal could take a unique path. These paths, once a problem, could now be used to send multiple independent data streams, at the same time, on the same frequency. This was revolutionary. A few weeks later, he filed a patent, increasing capacity in wireless broadcast systems using distributed transmission and directional reception, the first foundational patent for MIMO. Let's break down how MIMO actually works. In a typical setup, one antenna sends data to one receiver. This is called SISO, single input, single output. The data rate is determined by Shannon's capacity formula. K equals B times log, 1 plus SNR, where K equals capacity, B equals bandwidth, and SNR equals signal to noise ratio. To increase data, you need more bandwidth or a higher SNR, signal to noise ratio. But both are hard to scale. Enter MIMO. With 4 transmitting antennas and 4 receiving antennas, you can split your data stream into 4 substreams. Each antenna transmits one stream. Thanks to multipath, each stream travels a unique path. The receiver, using channel state information, untangles the jumble and reconstructs the full message. You've now just sent 4x the data, without needing more spectrum or power. And that's the magic of MIMO. But not everyone was convinced. At Bell Labs, researcher Gerard Foschini and colleague Mike Gans were running parallel experiments. Foschini mathematically proved that adding antennas dramatically increased capacity. Their system, BLAST, Bell Labs layered spacetime, validated MIMO in theory. But many in the industry were skeptical. Add antennas, quadruple speed? Sounds too good to be true, they said. But then came Wi-Fi. In the early 2000s, 802.11 grams could only reach 54 megabits per second. Not fast enough. Companies like Ergo and Atheros pushed the IEEE to adopt MIMO. And they did, with 802.11n, or Wi-Fi 4. This standard allowed up to 4 antennas, boosting speeds to 600 megabits per second, making Wi-Fi truly competitive with wired Ethernet. Meanwhile, Palraj started a company, Iospan Wireless. It built MIMO-based wireless broadband systems. Intel acquired Iospan's assets and used them to build WiMAX, a mobile broadband technology that would compete with LTE. But 3GPP, the mobile standards body, quickly adopted MIMO and OFDM into HSPA Plus and LTE, setting the standard for 4G. The result? An explosion of wireless speed. Phones jumped from 7 megabits per second to over 100 megabits per second, thanks to MIMO. By 2024, over 90% of the world's population received wireless data through MIMO-enabled networks. And the technology kept evolving. Massive MIMO. Bundles of hundreds or thousands of tiny antennas forming narrow beams to users. Beamforming. Targeted signal delivery. Line-of-sight MIMO. Precise antenna placement even without reflections. Polarization. Using vertically and horizontally polarized signals for more layers. Today, your 5G phone, your Wi-Fi 6 router, your smart TV, even your drone, they all rely on MIMO. Yet most people have no idea. Over 450,000 research papers and 570,000 patents have been published on MIMO. All thanks to one idea: turn a weakness into a strength. So the next time your video loads in seconds, or your call doesn't drop in a crowded street, remember, it's not magic. It's MIMO, the invisible engine powering our connected world.